Welcome to Fantastic Graph Types and How to Make Them for the R platform. This is Statistics Special Topics 20A. I'm Dr. Mark Williamson, Core Coordinator and Statistician for the Research Design and Compliance and Data Management Core for Transcend Translational Science engaged in North Dakota. Let's get into what we're going to do today. Our goal: to seek out and create lesser known but equally fascinating graphs. So we'll be covering 10 graphs today. We'll start with Violin plots, then Dumbbell plots, tree maps, Waffle plots, Dendrograms, heat maps, Kaplan-Meier curves, time series, donut plots, and funnel plots. Finishing out with a bonus of spiffing up the standards by combining or modifying sort of more classical style of graphs. So the R packages will be used today. Just to format things, we'll be using dplyr and tidyr, so part of the tidyverse. You can just load in the whole tidyverse if you want to. For data sets, we're going to use data sets, ape, or some of the trees. Stats2Data has a lot of data sets, and mass package. For graphs, we're going to do ggplot2 is our main one, but we'll be using alternative packages for some of the graphs, including Heatmap, Survival, GG's ServFit, Tree Mapify, ggalt, Waffle, and Meta. So with that out of the way, let's get started with our first plot. We're going to be looking at Violin plots. I'll start with a pretty basic example using the classic iris dataset. You can look at that with head if you want to, but then we'll use ggplot. So for all of these, I will save them as an object and then call that object to be able to view it. At the end of this talk, there'll be a link, and then there should be a link in the description of the video to all the code that I use for this on GitHub. So if you want to recreate this yourself, that's great. So for a Violin plot, it's pretty basic. So you use ggplot, set your data, and your aesthetics. You're going to need a y-axis, an x-axis, and then fill if you want to color it. So I'll use sepal length, and then our category of species and fill by species. And then with ggplot, all you need to do is geom violin. And this will pop up here. And I really like Violin plots because it's like a upgraded box plot because it shows sort of the density across the y-axis. So that's kind of nice. A little bit boring, so let's try a little more exciting example. So I'm going to use the diamond data set of characteristics of diamonds. Again, we're going to do the same setup, ggplot. We'll save that to p1b. Aesthetics, again, is going to be caret is going to be our numerical value, and then our category is going to be cut. We'll fill by cut, geom violin. But then what we're going to do here is we're going to custom color it, because cut, I want to use colors that sort of visualize the quality of the cut. So I'll do scale fill manual, the values. Start with yellow, green, and then these are, I believe, yes, bronze, silver, and gold when it comes to coloring. So just keep those in parentheses, and then we can call that. And this is what the Violin plot looks like. You see the cut here goes from fair, good, very good, premium to ideal. So I had ideal as gold, premium as silver, etc. And then we can see caret. And I really like this data set because it really can show you how it's distributed. This is a very large data set. You can see like with caret, you see a lot of the fair and good ones tend to be around 1 caret, which kind of makes sense. The nicer diamonds, they tend to actually be smaller. And again, you can see with the ideal especially, very large distribution at a very small caret. So the really ideal diamonds tend to be very small because it's really hard to get ideal cut diamonds at larger sizes. Or even like looking at caret 2, you can see there's almost none of the ideal. Definitely a little bit of a bump between fair and good at 2. So Violin plots give us a lot of information summarized across categories, a little bit more so than the traditional box plot. All right, let's move on to dumbbell plots, which are helpful to look at values like in the same category well, often across time or across some sort of other categorization. Now they're pretty cool, but they do typically take a little more work to get the data set up. So for the first example, pretty basic example, I'm going to use the MPG, the miles per gallon data set. We're going to look at transmission and year. So looking at the table, there's a lot of data here. I want to simplify it. So I'm only going to look at auto for transmission. So I'm going to create a new data set called NPG2. Subset that by just transmission, where the identity is auto I4. And we can pipe that using sort of the tidyverse style piping. And we'll use dplyr, select, and then I'm subsetting just keeping highway. That's highway mileage, the year of it, and then the model. And then from there, I'm going to pivot using pivot wider. Again, using this sort of the dplyr piping structure to create a new data set called NPG2 year. And we're going to have names from year, values from highway, ID columns is going to be C model. And the values function is going to be sort of this standard setup. And then I want names prefix of year, and then drop missing data. That's a little confusing here. Definitely look at the references if you want to look at another example of this. However, it helps to just sort of visualize the table we get out at the end. So what we get out is we get 11 models that have the highway mileage from 2008, and then also in a separate table from 1999, so we can actually compare the two and use it with a Dumbbell plot. And again, I subsetted this by only using ones with auto for transmission. So to create the Dumbbell plot, use ggplot, our new data set, NPG2 year. And now, slightly different with the aesthetics. You're going to use X as our older year 1999, and then we need this new optional statement, X end, year 2008. Then we can do Y model and then group by model. And then we can use the geom dumbbell built into ggplot2. And a lot of these are optional, but I like to fill this out here pretty straightforward. You can color things. For the X, color the X end. You can change size and do different dot guides, and then add labels. So I add the labels of highway fuel economy. Putting all this together, we get a simple but very nice Dumbbell plot here, showing the highway fuel economy. We can see for almost all the models, the blue is the 2000, the later year. That was it 2008, where like the light one is the 1999, and you see for almost all cases, highway fuel economy went up. For the Caravan two-wheel drive, and then the Tiburon, it did go down, but the rest went up. All right, let's do a little more exciting data. I am going to use radon measurement data, and so this is actually, I'm going to create my own data frame. This is based on real data that I've taken on some small experiments with groups and treatments, and because I'm formatting this data myself, I'm going to have it set up so that there's a group variable, treatment variable, and a before and after variable, two different columns so we can use the Dumbbell plot. And it looks something like this. Here's the head, so different groups, different treatments, and then before and after. So then we can use the ggplot setup here. Again, the X is going to be radon before, and then XN is radon after. Two different time points or treatment points, or however you do it with the Dumbbell plot. And treatment is going to be our Y and grouping variable. Again, I can do different colors and different setup for the dumbbell, which I'll do here. Create labels, radon level, but then what I'm going to do to sort of spruce this up, because I also have grouping, I'm going to actually do a facet wrap at the end by group, so I can look at this across the 4 different groups. And this is what I get. You can see the groups are the different boxes, so there's group 1, 2, 3, and 4, and then within it, they each have treatment. And this is kind of interesting. The radon after is the red. You can see for some treatments, like treatment A, looks like radon pretty much always went up. For other treatments, it sometimes went up, like for D, but the rest of the time went down and was often variable. You can see across different groups, things were different. Like in group 1, they all went up. In group 2 and 4, they all went down, except for treatment A, though for varying degrees, and then 3 is a little bit more up. 2 went up, 2 went down. So It's an interesting way to show differences between two values within treatments or within categories. All right, we'll move on to tree maps. Tree maps are fairly simple to do, especially because they're really for count data. So instead of doing something like a count table, tree maps is kind of nice. So I'm going to look at the survey data set, which has different variables, including handedness by sex. So I'm going to create a survey sum and really I just looked at the table and set this up so that we have left and right-handed, female and male sex, and then the count of those individuals with left or right-handed and then by sex. So then I have this simple data set, survey sum. I can use that in ggplot. And for under area, I want count. Under fill, I want sex, and then label by hand, and then subgroup. I'm not really going to do a subgroup, but I can also I could just leave this out or just make this as sex as well, so it won't differentiate. Then I can use the built-in tree map in ggplot, geom tree map, and then you can add some more characteristics like geom tree map text and tell it where to go. I'll get put in the center and bump the size up to 12. And what that looks like here, very simple. We can see that the ratio of sex is about equal, given the colors, the male and female being about the same size. And you can see here that most people are right-handed, few are left-handed, though slightly more men are left-handed than women. Let's do a little bit more exciting data set for tree maps. I'm pulling this from my understanding of shark orders. So I'm going to call shark sum. I'm going to create this. There are two shark super orders, the Galeomorphi and the Squalomorphi. And so I'm going to create super orders and then orders. There's not, there's 8 to 9 orders of sharks. For simplicity, I'm just using 8 orders here, from heterodontiforms to squaliforms, and then the count of species per order. So that's a data set here. And then I can use ggplot. Now this is going to be slightly different because I'm going to utilize the subgrouping here. Still pulling the data I want. Under aesthetics, area is going to be count again, because that's going to be the numerical counts. Fill is going to be order. Label is going to be order, but then the subgroup is going to be super order. You can create the tree map, the text like normal, but then the subgroup text is an additional statement, and I'm going to do a little customization there. I'm going to color that white, place it on the bottom left rather than something like the center, and then add some padding so it looks right, it doesn't overlap the borders. And then I'm going to create a geom tree map subgroup border and color it black. And when we get at the end of the day is this really nice tree map here. We can see the super order of Galeomorphi is on the left and the Squalomorphi is on the right. The different orders, different colors within the super orders. And see that Carcharrhiniformes is by far the largest group, has the most species in that order. Over in Squalomorphi, the Squaliforms is the second largest group, and we see there's some very small groups like the Heterodontiforms right there. So that is tree maps. Let's switch out to a similar sort of plotting method of essentially plotting counts across groups is a waffle plot. So start out very simple. I looked at the number of research universities across the US, R1s, R2s, and RCUs. And I did status and then states, just like the number within each group of this. And then I can just use from the Waffle package, I can use the function Waffle to set your data set, so research data set. You can set your rows. So I did rows 20 and then colors. And so I'm going to do green, yellow, and orange. And pulling this out here, get a very nice but simple waffle plot. You can see here that RCU is the largest grouping in orange here, where R2 is the smallest, and then R1 is mid-size. And you can change the amount of columns or rows to switch it up as you need to, but I think this is a good start. To make things a little more exciting, I'm going to create a more complex data set called arthropod data set. I'm going to be looking at arthropods. So I'm going to set classes of subphylum. There are 4 subphylums of arthropods. So I'm going to go from myriapods to hexapods. I'm going to have classes. I'm not going to actually use this in the end, the number of the actual names of classes, but I just have them there in case I want them later. And then I'm going to actually have what I call class categories. So for example, myriapods have 4 classes. So I'm going to say A, B, C, and D. Coeluroidata have 3, so 3. Crustacea have 10, so all the way from A to J, and then hexapods have 2. And then within each class, I've listed the number of orders of orders within that class. And then from there, I can create a plot. Now I'm going to actually switch over. We could use the Waffle function, but we can actually use GeoWaffle from ggplot. So I'll do that here. We have a little more flexibility. So put in my arthropod data set, fill by class category, and then values is going to be order number. In Waffle, I'm going to color it white, bump up the size. I'll have the number of rows to be 3. And then I'm going to, again, do facet wrap to look at multiple phylums at the same, or subphylums at the same time. And do the number of columns equal 1, so they'll kind of be right on top of each other. And then create this, clean things up, I'll use theme void. And what we get here is a very nice waffle plot here. Now, it is important to note what's been going on here. So these are the 4 subphylums, and you can see here, these are the classes. Now, unlike normal waffle plots, say Coeluroidata here, class A here, it's not the same as crustacean class A. These are different classes, but it's just like the numbering. So Coeluroidata have 3 classes, 2 very small ones, 1 larger one, where Crustacea has 10, and that's what's going on here. Or for example, hexapod only have 2 classes. One of them is actually Insecta. It's very large. It's the largest across all of them, and then the Enteroprocta is smaller. So that's a great way to use a waffle plot. Moving along here, let's get into dendrograms. So those are, you could also think of those as tree plots. And I'll start out simple with the US arrest data set. And now to plot dendrograms, to plot trees, you need to have the right objects. So I'm going to start with creating a new data set, taking US arrests and turning this into a distribution, a dist plot. And then I'm going to use hierarchical clustering on this with the method complete and save it as a new object. And then what I can do here, now I'm going to just use the simple plot function, which if you plot a tree object or just a dist object, it's going to automatically do it. But first I'm going to use shift the parameters so it'll show up. So I'm going to bump down the size a little bit, plot it, and then bump the size back up just so that it works for future plots, that it's not shifted. And simply, this is what it looks like, a cluster dendrogram. We can see here, these are arrest data based on different categories, things like murder, I think population size, assault, etc. And we can see how closely arrest statistics are among states, and some of these things sort of make sense. Something like Maine, South Dakota, North Dakota, Vermont, kind of sort of similar states have similar setups. Things like Colorado and Texas are closely clustered, or places like California, Illinois, New York, Michigan, they're clustered. So kind of an interesting way to see how data are clustered. Now, this was simple, but let's spruce things up by actually looking at what trees are more typically used for, which is like phylogenetic data, So we're going to take the data bird orders. You can check what type it is. It's in the right type. We don't need to reformat it. It's a tree object or a dist object. And then we can plot it. But however, first, I'm actually going to create a couple objects that I can use to customize the dendrogram. So I'm going to have this long chain of colors for bird colors for each of the different nodes, ranging from blue to black to red to green to purple. The sizes, most of the sizes are going to be the same. One is going to be bigger. EW and CW, this is going to be end weight and end color, and I'm going to change that out. And I look through the bird orders to specifically pick out which ones I wanted, and you'll see what they look like when we actually plot it. So again, we can plot bird orders using the simple built-in plot function. And then, because this is a tree, a dendrogram, I can set some specific options. So I'm going to have tip color. I'm going to use that bird color object that I made. The size is going to be bird size, edge width, and edge color, respectively. And so then for each of these different edges, tips, etc., I'm going to have a different setup based on what I made. And what it looks like is this here. And it's pretty cool. Let's go into what's going on. So these are the different bird orders that it's clustering by. And then I color them specifically, sort of by grouping. So this first group up here is purple, etc. I had them all the same size except for the passeriforms. That's the largest bird order. I made it larger just for interesting. And then say if you wanted to highlight a certain order kind of through the different branches, like say galliforms, I actually made these lines thicker and made it colored gold. So there's a lot of options you can use to customize your dendrograms. All right, a similar concept we're going to look into, which pulls in dendrograms on the side here, is heat maps. So I'm going to start again with the classic iris data set, though I'm going to turn it into a matrix as matrix, but then subset it so it's just going to be the values of like the sepal length, sepal width, etc., and not having the category what species in this matrix. So iris M, I can use the heat map function, scale it by column, change the size of the columns, and then I can use this option row side colors. I'm going to do rainbow 3 because there are 3 species, and then call iris species so it can color it by those different species. And what will show up here is kind of nice. So here's the heat map across the different samples. You can see sepal length, petal width, petal length, and then here's that row side colors. You can see here for whatever species red is, it looks like they all cluster together, whereas the other 2 species, the green and the blue, don't really, based on these characters, don't fully cluster together. They're kind of interspersed. So that's kind of interesting, but it would be nice to know like what the identity of the different species are. So we can turn to a new data set and actually use a different way to make a heat map. So I'm going to use the carnivore data set. You can look at it with the head. Essentially, it's different carnivore species and characteristics. I'm subsetting them. I'm only using a certain subset because there's a lot of missing data. So I excluded missing data and went from 112 to 91 samples and create as a matrix, taking out the identity of like superfamily, etc. And so then what I can do is use heat map. So we'll do it the first way here. Very similar here, though there's only 2 superfamilies. So we're going to say carnivore 2 superfamily. That's the roadside colors, and since there's just 2, we do rainbow 2. And then these are, I think the variables that we're using are abbreviated. So we're going to make my own label columns: female body weight, female brain weight, litter size, and gestation length. And when we do this, we get this here. Again, very similar to the iris. Kind of nice. I like the heat map part of it, but it'd be nice to know what's red and what's blue when it comes to the super families. So what we can do is we can use from the package pHeatMap the function pHeatMap. Fairly similar setup. We can have our data in, scale by column. We can actually adjust our clustering method. So I'm going to use average. We can annotate row. I'm going to do that here. I'm going to show I'm not going to show the row names because that's just sort of the individual observations. And again, I can use labels. It's going to be labels underscore column. I'm going to do the same thing here. And now when we have the heat map, now the heat map itself, now obviously you can modify this. You know, it's not quite as great, but I really like the fact that we can now label this as superfamily. So we can see that the blue is Caeniforma while the pink is Filiforma. And we can see here, and we saw in the early heat map that litter size and gestation kind of are a little bit different. But we notice here that the female brain weight and the just overall brain weight are very closely clustered. So probably didn't need both of those in this heat map. Same with the body weight and overall body weight. They're kind of saying about the same thing. A little bit redundant, and you can see up here, the dendrogram up here shows that those two are highly clustered. And then even higher up, the weight in general is clustered. So interesting observation. All right, let's change gears and look at some survival with Kaplan-Meier curves. These are looking at survival over time. So we're starting to get into time data. And so it takes a little bit more to set up, but once you get it set up, it's fairly straightforward. So first of all, you have to have data with the right kind of information. Typically, you're going to have some sort of time variable and then a status variable, which is going to be binary. So dead or alive, without a disease, with a disease, not failed, failed, etc. And so we're going to use the lung data set, looking at survival with lung cancer. And so what we need to do, I'm going to make an object called survival model. You need to use the survFit2 function with another function inside it, the surv function, which is going to take two arguments, a time variable, so time, and then a status variable, whatever it's called in the data set. In the lung data set, it's time and status. And then I'm just looking at overall, so I'm going to have a tilde and then 1. So that just says overall. To create this survival model, we're going to use the function ggsurvFit with our survival model. We can label things, so I'm going to do days and survival probability, and then you can add an optional confidence interval. And when we do that, fairly straightforward, Kaplan-Meier curve, we see survival probability starts at 1, and as days increase, that survival drops based on sort of the observations which hit that status of like, usually it's binary, like 0, 1, 1 meaning like died. And as time goes out, you know, this will go down to 0 eventually. Though most data sets aren't able to follow patients long enough that, or whatever situation long enough that all of them turn to 0. So often they'll just taper down. Now, this is interesting, but we can do better. We can look across categories. So we're going to use the veteran data set, very similar, create a survival model. But instead of a tilde 1, we're going to use a categorical variable here. So cell type. So we can look at survival curves across cell type. Because usually that's probably what you're doing with a Kaplan-Meier curves. You were looking at different survival rate across treatment, across group, across whatever. And so we can do the same thing here, label it, add confidence intervals, and voila, we get this. We can see here that survival differed. Squamous had the best survival, you know, the longest curve before it dropped off to 0, where something like, looks like adeno and small cell had a lot steeper curve. So like more people were dying faster. They were surviving less or a shorter survival time. So that's gives us interesting information here. All right, on to our other time type of data, time series. And these are pretty straightforward, but sometimes you have to format the data here. So I'm going to start with Apple stock. Now, it turns out if you try to just run it with a genome line from ggplot off the bat, it doesn't work. You have to make sure that the date, so working with dates in our date data in general can be a little bit finicky. So to make this work, you can look at Apple stock date and then reset it as date using a specific format so it actually fits. So at least for the Apple stock, the format needs to be month/day/year. And when you actually do that, and it's in the correct date, you can just use ggplot X equals date, Y equals whatever you want. This, in this case, this is price. And then we can just use geom line. And I'm just going to set line width, but otherwise keep it straight. And we get a nice time series here. We see that the date, we can see by default, it does in about looks like half a month. So August, I mean, tick marks by month, but then the grid in the back by half month. We can see here, the stock price rising, dipping, etc. Now, we want to be a little more exciting. I'm thinking about time series. I've got more radon data. And again, this is real data that I just pasted in here. If you want to go and use this yourself, use the R code, you can just run this and you'll get that radon 2 data set. So I have different treatments, and this is slightly different data here because I have across hours. So I'm going to have 4 different treatments over 24 hours and then repeat it 24 times, and then are all the data here. And what I can do here, then I can use ggplot2, hour, radon, and now I can add a group variable because I have those 4 categories of treatment. Here, we can do geom line. I'm going to do some aesthetics to color by treatment because otherwise the color won't be there, and then have a normal line width of 1.0 to make it a little thicker. And then we get a very nice time series by treatment. We can see that it's pretty jangly data across hour rather than say months that Apple stock was. And as we see, it generally goes up in everything, though with various treatments it goes up less. So treatment C went up less, though it did start at the lowest area, whereas something like treatment A and B sort of were vying for the top place here. All right, we'll turn our attention now to donut plots. So donut plots are essentially pie charts, pie plots with the middle taken out. Typically, pie charts aren't the best to visualize data, and donut plots fall into that same problem, but they are interesting to make. And I think when we get to the more exciting side of things, I have presented a helpful and not problematic way of using them. Anyways, but just to see how you do them in general, there's a couple different ways. Donut plots, besides being so simple, like a very simple data set, you're just showing essentially proportions across a group, different categories. It's not a lot of data there. It's surprisingly hard to make, so that's maybe another reason to not even use them. Anyways, that being said, let's see how we can put some together. I'm going to create a data set called science funding. So essentially it has two setups. It has categories, so different institutions. I looked at the NIH, NSF, and DoD. I think this is for 2023 or 2024. Really doesn't matter. It's the funding in billions of dollars across the 3 groups. So just 3 categories, 3 counts of funding. Now, to get it to plot more easily, I'm going to create some additional variables in here. I want proportions, Y max, Y min, and then label position. So I'll do that here. For proportions, I just take the funding divided by the total funding. I can do the Y max, use the proportion that I generate here to get the cumulative sum, Y min, again using the Y max, and then the label position using these variables here. And what I get, it's always helpful when some of these things are going on here just to look at what we're creating. So we can see these are the 3 institutions. Here's the proportions and the Y max and Y min. So we're getting from 0 to 6.5 to 6.8 to 8.4, and then 8.4 to 1. So we get it across, from 0 to 1. And we can get the label position, make it a little smoother. So what we're going to do, this is one way to do it, is use ggplot, get our data, and there's going to be a lot of statics. We need a Y max, a Y min, an X max, an N min. So the Y come from our data set, our X. That tells you how thick the donut is. We're going to do 4 and 3, so hard code it, and fill by institution. Then we're actually going to use the geom rectangle. So essentially we're making rectangles, but then we're going to throw them into a polar coordinate, which the option we need is coordinate polar, theta equals y. We can do our x limits. Again, that'll kind of help set up how big this is. we'll do geome label at 3.5, so right in the middle sort of these actual donuts. And then the actual position is from our data set, label position, and label by funding, and bump up the size, and then theme void to sort of clean things up. And donut plots come out looking like this. So we can see the NIH has the largest funding at 37 billion. NSF is the least at 7, and then DoD at 10. Of course, you could modify these things. You can do percentages, etc. But here we go for a simple donut plot, which probably would be better just as a bar plot. But something I think could be useful for a donut plot in a more exciting fashion is actually, I'm thinking of genomic data. More specifically, things like prokaryotes, which have circular genomes. It might be useful to use donut plots to create a graphic of a circular genome and maybe then points along it of note of like distribution. So that's what I'm going to do here. I'm going to create a data set called genome donut. So essentially, I'm going to have different segments, A, B, C, and D, values, patterns, this to label it. Don't get too hung up on all these numbers here. You can put it in your own, but you can choose mine here and tweak them. We're going to use object h size 4, and then we're going to, with the genome donut, we're going to mutate it and then add x as h size. This will make sense when we get to the next step here, because then we're using a slightly different setup with ggplot to create a donut plot, and we have more flexibility to make it our own. So we're not going to use rectangles. We're going to use geome columns, or geome col. So we're going to need to have our x is going to be the h size. That's going to be how big or essentially, yeah, how thick or thin it is. Y is going to be our value from our data set, and then fill is going to be segment. Coordinate polar again to polarize it to make it a such circular. X limits to set up more things here, and then the geome color. And then what we want to do here is scale fill manual to have colors ourselves here. Essentially, this C3 repeating, that's a gray, and then I have some green. And actually, because I have different patterns, I'm actually going to facet rat and then number of colors 4, so they'll be in all in a row together. I can do a bunch of theme stuff, mostly just to blank things out to keep it nice and clean. This is all sort of optional, but when we get to the end of the day here, this is what we get. And I really like this. So these are different options, and I've colored them green. So like maybe this is one segment of a genome that you can think about, different segments, different distributions. So it's a lot of work, and it's a little low res, but you can certainly use donut plots for more than just pie charts with the middle taken out. All right, let us switch over to funnel plots. Now, funnel plots are probably one of the most bespoke graphs we'll be looking at today. Typically, they're used to in like meta-analyses, and it helps like figure out with like publications, with like studies, whether there's like selection bias, etc. And so I'm not going to go too much into detail of these. You can look at the references I have here. I'm mostly just trying to get this off the ground. So a lot of this I think comes from like the data sets, and also the functions come from the meta package. So we can look at the Oakland 1995 data set. We're going to need to actually format, I'm calling it Olkin2. You need to use a function metabin to bit it in such a way that the funnel function can work with it. There's different variables here. The data, you're going to need to paste author and year so it can be labeled. The study label can be proper. There's different options. You can do relative risk. That's what I'm going to do here. And once you have this data set, you can just do funnel Oak2. So most of the work is done on getting the data set correct. And when you do that, this is the funnel plot here. And so the RR method was risk ratio. You can see here that looks like there's a fairly, and these dots are the different size, fairly decent distribution across the risk ratios. So you can do more with funnel plots here. So I'm using the data caffeine. I think this is a fictional set of data about caffeine usage. but doesn't make that any less fun. You're going to need to use meta-bin again across different variables. Again, you need labels, and then I'm going to do odds ratios for this. And then now you can do a very simple funnel, or you can do a lot. There's a lot of options to tweak the funnel plot. So you can use caffeine too. You can use different levels. You can add contours. You can color the contours. You can change how your points look like. You can change the size. You can change the shape. You can add a legend. If you do all that, you can get something like this. You can see here that there's an outlier over here. There's sort of our contours and our legend, and these are the odds ratio. So a lot you can do with funnel plots, especially if you're looking at meta-analyses. All right, with that, we've come to the end of our normal time, and let's do some bonus where we sort of spruce up some of the more standard. So let's start with stacked bar plots. Typically, you have bar plots that are staggered if you want to compare, but sometimes stacked bar plots are really helpful, especially things like ecological data or especially genomic data where you're looking at like abundance and distribution across sites. So I'm going to create a crustacean data set. Now, the classes are real. We're going to bring those classes back from our earlier one. There's 10 crustacean classes, so I'm going to call it P class. So phylogenetic class, because class is as a statement is already used. And there's 10 of them, and I'm going to have 10 fictional stations where someone's, say, sampling and getting the number of species or the number of observations, and that's going to be under counts. So each station will have 10 samples, and then each station will sample across the 10 classes. And so then I can just check the overall number per station by using the piping, doing the group by sample, and summarize some counts. I'm not keeping this as a data object because really I just want the number by the 3 different stations. So A turns out to be 168, B is 151, C is 241. Then I can add that to my data set, crustacean D sums, repeat it 10 times. So for each observation, we have the sum here. So 168 for stations A, 151 for stations B, and 241 for stations C. And then I can calculate percents from there by just taking counts divided by the sums. And with that in hand, we have both counts and percents, and we can look at 2 different types of stacked bar plot. The first one, we're going to use ggplot, very straightforward here, sample, counts, and fill by P class. We're going to use geom_bar. We don't need to have any specific aesthetics, and we do need to make sure position is by stack. I think that's by default, but you can also clarify that, and then stats identity, and then because we're with counts, this is what we get. We have the different stations, we have the different counts of the different classes, and by the different colors. It's kind of cool here. You can see station D had the most overall. It looks like Malacostracia was, for the most part, the highest in all of them, though copepods were also fairly high. Again, this is fictional, but kind of going on a vague notion of general abundance and diversity. Now, it's kind of nice, but it's sort of hard to directly compare across stations because the overall counts are different. So it'd be nice to have percentages, which we already calculated. So we can do another plot. Instead of counts, we can just use the y variable as percents. And the data here then looks like this. We can see here it goes from 0 to 1. So we have equal. So this is now by percentage rather than raw counts. And then we can better compare it. We can see here that in station A, which didn't have as many, but we can see that the Malacostracia had the highest percent in station A. We can see that ostracods were most abundant by percent in station B, etc. So it's a little bit more comparable, and that's typically a stacked bar plot with percentages. So all the bar plots are the same size. Is pretty common, especially for like genomic, like amplicon sequencing across samples or types. All right, another bonus is adding plots together, like the dot and box plot, able to give 2 kind of summaries at the same time. So I'm going to use the diamond data set again. However, because it's such a large data set and can be kind of hard to see things, I'm actually going to restrict it. I'm going to call diamond 2 to just diamonds, just very large diamonds, essentially diamonds of carats of greater than 2.5. And so that'll be a little bit easier to parse out. That's a much more limited data set. Anyways, I'm going to ggplot. Y is going to be our carat. X and fill is going to be cut. And then I'm going to do a geom box plot. So it's going to have cut by the categories cut and then the carats. So we saw that with our violin plots, but now these are going to be box plots. However, then I'm going to create a dot plot or points using geom points over that. Aesthetics with color by price now, so we can see price. Can change the size and shape. We're going to jitter the position so they're not stacked on top of each other, so we can see a little bit more of the individual values. And then we're going to do scale fill manual to manually fill in the different box categories. Again, using the same categories we used for the violin plots. And then scale color gradient, color the different points because those are by price. Low being green, high being red. And with all that together, we have a very detailed plot. You see carat here, again, starting at 2.5, going up to 5. The bar plots, again, are the cut. You can see more the distribution here. And then the dots are the individual points. And then we also color them by price. And so some of these interesting comes out. So only the fair ones had really high carats, and then unsurprisingly, those are very big diamonds. They tend to be red, very expensive. Same with like some of these ones over here, especially premium ideal. They tend to be redder. They tend to be more expensive because they're nicer. But some interesting things point out here. You notice these two ideal diamonds up here that are actually very large carat, like above 3. They're only sort of an intermediate price, which means there's probably actually more going on. Maybe these are not colored nicely, or there's some other thing that keeps the price from being astronomical. So this gives a lot of information they're able to put together to summarize what's going on with your data. All right, our final bonus is multi-level regression. So you think of regression, you have an X and a Y axis, which are numerical, and then you plot a regression line, which is great, but maybe you have multiple levels. That is, you're looking at regression across different groups. So it's nice to be able to have more than one line. And actually, this is fairly straightforward to do using geom point and geom smooth. So I'm going to go and take my radon 2 data set because I knew that was hour, so that's numerical, and radon level, which is another numerical. I'm going to look at hour and radon, and I'm going to group it by my treatments because I have those treatment groups. I'm going to use geom point, color by treatment, but then I'm going to use this geom smooth, which lets you add a type of line. So I'm going to use the method linear model, which is fit a linear model to it, and then formula y equals x. But then I'll color by treatment, and so for each treatment we'll get its own line. And then this is SE standard error, and then we get a nice level regression line. And what I really like about this is this pulls out not just a single regression line, a regression line for each treatment, and each treatment can have its own intercept and its own slope. Though if you notice here that the best fit lines here, they're all about the same slope. The intercept is different. So treatment C starts at the bottom here, but you can see that the slope can change. I mean, it's hard to see with these other ones, but with A and D, you can see here, actually their intercept starts about the same, but the slopes are different. Treatment A has a steeper slope. So that's kind of nice, but I wanted to create an artificial data set to really show how freely the different treatments can vary if the data is there. So I'm going to create this test radon, just fake data set here, 4 different treatments again against just 10 hours. But then I purposely created data here to make very different slope and intercepts. You can do the same sort of thing here to plot this, and this is what I get here. And so you can see here, for my treatment B here is essentially a flat line. There's no real change. Treatment A had a high increase. Treatment C, while started about the same as treatment A, had a very shallow slope. And in fact, treatment D had an inverse slope. And you can see all this sort of information on a plot here using geom point and geom smooth. All right, that's all I have today here. These are all the references I use for this video. They should also be in the description. This training was done under Transcend, part of the grant from the National Institute of General Medical Sciences. So if you find this useful, please cite Transcend. Thanks. Have a great day.